Welcome, everyone, to TechDaily.ai. I'm your host, David, and joining me today is our expert, Sophia. You can sponsor this podcast for just $25. Your message will be featured across major platforms like Apple Podcasts, Amazon Music, Spotify, and more. If you're interested, visit TechDaily.ai to get started today.
Hey, it's really great to be here.
So, if you have ever owned a laptop, you know that quiet, simmering dread of a dying battery.
Oh, yeah. Watching that little icon in the corner of your screen just drain faster and faster.
Right, until you realize your machine can basically barely hold a charge for 20 minutes.
It's the worst.
It is. And for over a decade, the industry's solution to that problem has essentially been a brick wall. Like, fixing it meant either paying this eye-watering repair bill to the manufacturer or simply tossing the machine into e-waste and, buying a brand new one.
Exactly. It was a completely closed loop.
But today we are unpacking a really fascinating topic, specifically looking at Apple's new, highly affordable MacBook Neo.
Yeah, and the real buzz around the Neo isn't actually about its processing speed or the screen.
Right, which is usually the big selling point.
Exactly. The big story here is a radical shift in how the machine is physically put together. It's marking this massive change for consumer hardware.
And our mission today is really to figure out why one of the most influential hardware companies in the world just suddenly reversed over a decade of rigid, inaccessible design philosophy.
Because, the Neo initially just got attention for its price tag. It's positioned as the most budget-friendly MacBook on the market by a pretty wide margin.
Which is great on its own, right? But then the hardware analysts actually opened the chassis.
Yeah, and the narrative shifted completely. The teardowns, especially a massive structural analysis by iFixit, revealed a fundamental change in the internal architecture.
And didn't iFixit actually declare the Neo to be the most repairable MacBook released in about 14 years?
They did, about 14 years, which in tech years is basically an eternity.
That is wild. To really understand the gravity of that 14-year benchmark, we have to look at how laptop design has evolved. Because for years, I have compared modern hardware design to like a beautifully sealed, impenetrable vault.
Oh, totally. Just a seamless slab of brushed aluminum.
Right. There are no visible screws on the exterior, no clear seams, no obvious entry points. It's this aesthetic masterpiece that aggressively whispers, look, but do not touch.
Yeah, that vault design is the direct result of an industry-wide obsession with the Z-axis.
The Z-axis, meaning like the thickness?
Exactly. The relentless engineering pursuit of shaving just millimeters off the thickness of a device. Because if we look back to roughly 2012, before the ultra-thin unibody designs completely took over, laptops were actually highly modular.
Oh, I remember. If your battery died, you just flipped the machine over, slid a little mechanical plastic latch, and popped a new one in.
Right. But to achieve the microscopic thinness we see today, engineers basically had to eliminate those bulky plastic battery enclosures and the latches.
And that transition wasn't just about making the laptop look sleek on a desk, was it?
No, not at all. By removing those enclosures and gluing the raw lithium-ion pouch cells directly to the internal aluminum casing, the battery essentially became a load-bearing element.
Wait, really? The battery was load-bearing?
Yeah, it added crucial structural rigidity to a chassis that was suddenly so thin it might otherwise just flex or bend under the weight of a user's palms.
Wow. So that structural integration is what actually sealed the vault?
Exactly. Manufacturers, led largely by Apple initially, but followed by everyone else, began using industrial-grade adhesive to bind the internal components together. The battery was fused into the skeleton of the machine.
So when the teardowns highlight that the Neo is the most repairable machine since that 2012 era, it means we are seeing a deliberate reversal of that skeletal integration.
A highly engineered reversal, yeah. Which brings us to the biggest revelation from these reports. The battery itself.
The most dangerous component inside that chassis.
Without a doubt. The engineering reveals that Apple didn't just tweak the layout. They fundamentally altered the extraction mechanics. They finally abandoned the industrial adhesive.
Okay, so if there's no glue holding the battery in, what's securing it?
A dedicated metal tray. And that tray is secured to the frame by exactly 18 individual screws.
18 individual screws.
Yep. And the reaction to this specific choice was universally enthusiastic.
Really? On the surface, telling someone they have to carefully extract 18 microscopic screws sounds incredibly tedious.
Does it sound like a lot of work?
It sounds like assembling a highly stressful piece of miniature IKEA furniture, where one wrong move means you lose a vital piece in the carpet forever.
Yeah, I get that.
So why is trading glue for 18 tiny screws considered such a monumental victory for the average consumer?
Well, iFixit explicitly concluded that mechanical screws will beat industrial adhesive every single time. And they noted that discovering those 18 screws actually sent cheers across their office.
Gears over screws.
Yes, because the difference lies entirely in predictability and safety. When a lithium-ion battery is glued down with high-strength adhesive, removing it is literally a hazardous extraction mission.
Because you can't just pull it out.
No, absolutely not. You have to introduce chemical solvents like high-concentration isopropyl alcohol or acetone into the chassis to weaken the glue's bond.
Which means you're pouring liquid chemicals into your electronics.
Exactly. And then you have to use plastic pry tools to physically wedge the battery away from the metal frame.
Which means you are applying sheer unpredictable force to a volatile chemical pouch.
Right. And if your pry tool slips or if the adhesive is stronger than you anticipated, you risk bending or puncturing the lithium-ion cells.
And a punctured lithium-ion cell is bad news.
Very bad news. It rapidly leads to thermal runaway.
Which is basically a fire, right?
It is a violent chemical fire right there on your workbench. So the glued-in architecture created this massive psychological and physical barrier. It felt dangerous to the consumer because it inherently was dangerous.
That makes total sense. But a screw, even 18 of them, totally changes the physics of the extraction.
Exactly. It converts a high-risk chemical process into a low-risk, predictable mechanical process.
You apply a specific amount of torque to a screwdriver, the screw turns, and the fastener releases.
Right. There's no guessing game about how much the glue has dissolved, and no risking a localized fire in your living room.
Plus, by using a metal tray secured by those 18 points of contact, Apple maintains the structural rigidity of the chassis we talked about earlier.
Yes. The force is distributed evenly across the metal tray rather than relying on the sheer strength of glue. It keeps the frame stiff while still allowing the entire assembly to be lifted out safely.
So that tray acts as like an intermediate layer protecting the volatile cells.
Exactly. But the internal overhaul extends far beyond just the battery bay.
Oh, what else did they find?
The teardowns also detailed a massive architectural shift in how the components are layered. They highlight what engineers refer to as a flat disassembly tree.
A flat disassembly tree. Okay, so in previous unibody designs, I know the internal layout resembled basically a Russian nesting doll of electronics.
That is the perfect way to describe it.
Like if you had a failing keyboard and needed to swap it out, you couldn't just access the keyboard.
No, you had to remove the bottom casing, carefully extract the glued-in battery, disconnect the thermal fans.
Wait, you had to take all that out just for the keyboard?
Yeah, you had to completely remove the primary logic board just to reach the keyboard assembly at the very bottom of the chassis.
That is insane. It required dismantling the entire ecosystem of the laptop to fix one isolated issue.
Exactly. But a flat disassembly tree completely flattens that hierarchy. By redesigning the internal cable routing, components in the Neo are heavily modularized.
So the flexible ribbon cables are routed differently now.
Right. They're now routed around or over primary components rather than trapped beneath them.
So if you need to replace the trackpad or the keyboard on the Neo, you can bypass the logic board entirely.
You can. You can access the specific part you need much more directly, without disturbing the delicate connections of the surrounding hardware. Even the display hinges and connectors have been redesigned to detach with way less intrusion into the main casing.
Okay, so the physical roadblocks have been systematically dismantled. The internal map is easier to navigate, the cables are routed logically, and the hazardous glue is gone.
It's a massive physical win.
But physical hardware is really only half the battle in modern electronics, isn't it?
Oh.
We also have to talk about the digital locks.
Ah, yes. The digital locks. This is perhaps the most crucial element of the entire redesign because the teardown analysis revealed a massive shift in the software architecture as well.
Right, because for years, manufacturers have utilized a practice known as parts pairing.
Yes. Parts pairing is a system where the logic board of a device is digitally linked to the unique cryptographic serial numbers of its surrounding components.
Like the display, the biometric sensors, or the battery.
Exactly.
I always think of it like the logic board is acting as a bouncer at a highly exclusive club.
A bouncer, yeah.
Yeah, and it's checking the cryptographic ID of every single part before it lets the laptop boot up properly.
That's exactly how it works. In the past, if you successfully managed the physical repair, let's say you swapped out a cracked screen with a genuine, perfectly functional replacement screen from another Apple laptop, the logic board would realize the new screen serial number didn't match the original guest list burned into its memory.
And when that happened, the software would aggressively retaliate.
Oh, heavily. It would lock you out of certain display features like True Tone, or it would constantly bombard your operating system with warning notifications.
Claiming the part couldn't be verified, even if it was an identical, authentic component.
Right, and to update that cryptographic guest list, you previously needed access to proprietary cloud-based calibration tools that were strictly limited to authorized technicians.
But the analysis of the Neo shows that Apple's native repair assistant software has been updated. It now handles these handshakes locally.
It does. It now appears to seamlessly accept replacement parts.
Wow. So it updates the cryptographic ID without throwing up warning messages.
No warning messages, and without artificially disabling features. By allowing the repair assistant to validate parts locally, the manufacturer is basically tearing down the invisible digital barriers that have historically thwarted independent repair.
That really democratizes the entire ecosystem.
It does. It means that a local independent repair shop down the street can now perform a screen swap or a battery replacement without needing to pay exorbitant licensing fees.
And without needing complex software workarounds, which directly challenges the practical application for you, the listener.
How so?
Because even with the flat disassembly tree and the mechanical screws, the reality is that not everyone is going to want to open their laptop on their kitchen table.
True. It's still a delicate piece of electronics.
All right, but by dropping the digital roadblocks, the power is still returning to the consumer. If you don't want to wield the screwdriver yourself, you now have the freedom to take it to a local technician.
Who can do the job faster, safer, and at a fraction of the cost of an official manufacturer repair?
Exactly. The elimination of those software locks fundamentally changes the ownership dynamic.
It really does. However, we do need to look at the other side of this. The teardown reports provide a necessary counterweight to this newfound modularity.
Right, there is a catch.
A pretty significant one. As transformative as the battery tray and the flat disassembly tree are, the Neo still harbors some major hardware restrictions that prevent it from being a fully modular, future-proof machine.
And we're talking about the primary computing components here.
The structural analysis confirmed that both the system RAM, the memory, and the solid-state storage drive are completely soldered down to the logic board.
Soldered down. So to use an automotive analogy, we are basically looking at a machine where it is incredibly easy to change the tires, swap out the windshield, and replace the battery, but the engine block itself is completely welded shut.
That is the perfect analogy, and that integration is driven by the shift to Unified Memory Architecture, or UMA.
Right, because by soldering the RAM directly onto the silicon package, placing it just millimeters away from the processing cores, engineers achieve these staggering improvements in bandwidth and latency.
Exactly. The processor doesn't have to reach across the motherboard to retrieve data from a separate stick of RAM. It is all instantly accessible within the same microscopic footprint.
And the performance gains of unified memory are undeniable.
They are, but it entirely sacrifices long-term adaptability.
Which is the frustrating part, because
Right.
if you purchase the base model of the Neo today, and 3 years from now, your workflow evolves. Maybe you start editing high-resolution video or compiling massive data sets, and you suddenly need double the memory to keep the machine running smoothly.
You are physically locked out. You cannot open the chassis and snap in a new RAM module or a larger hard drive.
You are permanently tethered to the exact specifications you chose at checkout.
Precisely. The only solution for needing more computing headroom down the line is to purchase an entirely new laptop.
Which feels like a step backward compared to the battery.
It is, and this limitation is exactly why the iFixit teardown, despite praising the removal of adhesive and software locks, ultimately awarded the MacBook Neo a repairability score of 6 out of 10.
Now, a 6 out of 10 in almost any other context sounds like a barely passing grade. Like if we were evaluating a bulky modular desktop tower, a 6 would be a massive failure.
Oh, absolutely. But the teardown specifically noted that within the context of the ultra-thin laptop market, a 6 out of 10 is actually a remarkably strong score.
Really? A strong score?
Yeah, because they are grading on an incredibly steep historical curve. For the better part of a decade, these ultra-thin unibody machines consistently scored 1s or 2s out of 10.
1s or 2s?
Yeah, they were engineered to be impenetrable, disposable appliances. So to leap from a 1 to a 6 represents a profound philosophical U-turn.
Okay, I see. So yes, the soldered memory and storage are frustrating bottlenecks that cap the performance lifespan of the device.
Right.
But the physical lifespan of the hardware itself, The parts that inherently degrade over time, like the battery chemistry, the keyboard switches, and the display hinges, that has been dramatically extended.
Exactly. It is a deliberate compromise between performance architecture and physical sustainability.
You gain the ability to maintain the physical health of the machine indefinitely, even if you cannot upgrade its cognitive capacity.
Beautifully said.
So when we step back and synthesize all of this, the MacBook Neo presents a really fascinating duality for the market.
It does. It pairs an unprecedented budget-friendly entry price with a level of structural accessibility we haven't seen in over a decade.
Engineers traded hazardous industrial glue for predictable mechanical screws. They flattened the internal cable routing to modularize the physical parts, and they dismantled the cryptographic software locks that previously punished independent repair.
Yet it simultaneously enforces a strict ceiling on performance through its soldered unified memory architecture.
Requiring consumers to accurately forecast their computing needs years in advance. Which means the next time you are in the market for a laptop, you have to critically weigh your priorities over the lifespan of your tech.
Yeah, you have to decide if the initial affordability and the comfort of knowing you can easily replace a degrading battery in 4 years outweighs the inability to upgrade your storage or memory as your demands grow.
It forces a much more intentional purchasing decision. The industry is providing the mechanical tools to extend the life of our hardware, but they are leaving the performance limitations firmly in place.
And that leaves us with a really provocative dynamic to watch unfold.
It does. Because if a dominant player in the hardware space is willingly moving toward highly repairable designs on their most accessible machines, how long will it take for the rest of the industry to follow suit and make modularity the global standard again?
That's the big question.
Right. And more importantly, now that the beautifully sealed vault finally has a keyhole, will the average consumer actually take advantage of their right to turn the key? Or have we become so culturally conditioned to unboxing shiny new hardware that we will simply keep replacing our devices anyway?
I guess we'll just have to wait and see.
We will. Well, thank you all for joining us on this exploration of laptop engineering and design. We will catch you on the next one.